Okay, hello everybody. Right now we are up to the next part of our calculus lesson, which is looking at more at 8a and 8b, which is the first principles. So if you have not looked at the previous lesson, which is above that on our notes, which we started with 8c, you need to go back and have a look at that first, I think, a little bit of understanding of what we're doing or why we're doing stuff before we do these first principles. Okay, this section introduces a limiting process to find the gradient of a tangent at point P. That's what we did in 8c above. We differentiated, and what we were finding was the gradient of a tangent at a point. So we're doing the same thing here. We're just doing it, I guess, from basic principles. This will be the formal definition of the derivative, and we call it differentiation by first principles. So what we need to remember, and what you guys need to remember, is the language that we're using. And we're talking about differentiating. When we're differentiating, we are finding the derivative. So they're both the same thing. They're just different words that we're using for that. Let's go down to the graph a little bit below and have a look at what's happening down there. Remember, everything actually relates back to a graph in calculus and in functions. So we've got our x and y axes. We've got a function on there, and that's that black line. And what we've got on that function are 2 points. We've got a point P and we've got a point Q. And what we've got between those points, P and Q, is a line, and we called that last time a secant. I don't use that word very often. So the red line's a secant. And what we're wanting to find, our first principles rule, what we're going to use that for is to find the first principles rule for the tangent at P. But we're going to start off with a secant, and we're going to get down to the tangent. Okay, so let's define what our points are. So we've got our point P here, and it has our x and y coordinates. Remember, our x coordinate is just, we're going to call it x, and our y coordinate is f of x. Okay, so x, f of x is what we're going to call point P. We have a look down here. That can be any point on the curve. We've got our point Q up there as well. Q is another point on the curve. And to get to Q, which in this case it's to the right of P, it could be to the left of P, it's just any other point on that curve, we're going to add a little bit extra. So we're at x for P, we're going to add a little bit called h. It's a tiny little bit. So x plus h will take us up to that x coordinate of Q. And then if that x plus h is substituted into our function, we get f of x plus h. So our point Q has the coordinates of x plus h and f of x plus h. We might pop those 2 points down there for us. So P is x and f of x, and Q is x plus h and f of x plus h. That's how we're going to define it, just 2 points on the curve. Now, if they were to any other points that we had worked with previously, we could use those to find our gradient. So remember, our gradient of a line is our rise over run. So we could still use that formula, rise over run, to find what the gradient of that secant is. And that's what I've got us to do below down here. So I've said that the gradient of the secant PQ, or basically it's just a line, so you can call it the line PQ, is rise over run. Remember, that was also, we had used the y2 minus y1, x2 minus x1 formula, which was what we've done. So our rise is the up and down part, okay, between those 2 points, and that's the difference between our f of x plus h and our f of x. So we've got f of x plus h, take away f of x. Over our run component, okay, between those 2 points, that's in there. So to get that distance, we're going to have x plus h, take away x. And I've done that on the bottom. X plus h, take away x. Now the top line we're going to leave as the same because I can't change that. So that stays as f of x plus h minus f of x. But on the bottom, if I was to remove that first bracket, I've got an x plus h minus x. The x's cancel, and I'm just left with h. And that's going to be the main part of our formula for differentiation by first principles. Is this part here. And what we're going to say, or I guess what we want to have happen, if we go back to our graph, is we've got a secant PQ, but we know by definition that when we differentiate, we're finding the gradient of a tangent. And the tangent is the green line. So we want to turn that red line into a green line. So what really would be happening is that Q point there is going to get closer and closer and closer and closer to P until it's just about P. So this distance H is going to become smaller and smaller and smaller. Small as it can go. It's going to get closer to 0. And that's what we've done here. What I've written here is as H goes to 0, this H, which is our H distance here, brings that Q down to P. So H is going to 0. And as that happens, the point Q moves as close as we like to P. And the gradient of the secant PQ becomes as close as we like to the gradient of the tangent at P. And that's where our first principles formula comes. So basically, as Q comes close as we want to P, it basically only becomes P, and we're going to take the green line then instead of the red line, and that's our gradient of the tangent. Here's the formula we came up as, but H is going to get really close to 0, but it can't be 0 via this formula because we can't divide by 0. It's just going to go towards 0. So what we're going to use for our first principles formula is that for each value of x, the derivative f dash of x, remember that's the formula we used, or the formation for our derivative last lesson, f dash of x is defined as a limit as h goes to 0 of f of x plus h minus f of x over h. So this is the first time we've used this function, the limit. Okay, and that's all it's telling us is h is getting smaller. It's as close as we want to p. I'm going to find what that's going to be, but it's not actually going to get to 0. We'll need to remember that one. We need to remember that one as that one is not given to us on our HSC formula sheet. Okay, so let's go and have a look at some questions. So this is the kind of thing that you could be asked. Generally it comes through in, or it has previously come through in a HSC question as a more of a multiple choice style question, okay, or a low mark answered question. So they're not difficult questions, these ones. It's something like what you may end up with. If f of x is equal to x squared, use first principles differentiation to show that f dash of 5 equals 10. So the key word there is your first principles differentiation. So let's start by writing down our rule for that. Okay, there are a couple of ways that we can do this. We can go straight and work through with our x's, which is the way I normally do it, or we could put our 5 straight in now and work with that. So I'm going to do it my usual way, but we could also look at it at another way as well. So f of x plus h means wherever there was an x, we're going to replace it with x plus h. There's our function, so we're going to start with x plus h squared. That's our f of x plus h minus x squared. That's our f of x. And it's all over h. So we need to expand that first line. However you expand that, whether you double the brackets out and FOIL it, or remember we square the first, square the last, 2 times the first times the second. Back to our original topic. However you do that, pause the video and do that now for me. Just make sure your top line looks like mine once you've grouped together like terms. I'm going to continue up here. These parts are going to cancel out. Okay, so what you can see, there's a h on the top line and a h on the bottom line, so I need to factorise out that h on that top line. Okay, just pause it if you need to, checking that you can do that. The h's cancel out, and I end up with f of x is 2x plus h. My question was wanting f of 5, So I'm going to put that 5 in there now. 2 times 5 plus h, which equals 10 plus h. Now, remembering with our first principles, what we should have been doing was limiting or looking at our limits as h goes to 0. So if h is going to 0 here and getting tinier and tinier and tinier, what we're left with is just our 10. That's our answer. F dash of x equals 10. We're just remembering it's taking our limit as h goes towards 0. We don't want h to be 0. We're not actually just subbing in 0. We still need to have a small amount of h, but h might be a tiny amount, like 0.0001, but it's not actually going to be equal to 0. Let's have a look at our next question. Example 3, part A. Use first principles differentiation to find the derivative f of x equals x squared, which is what we have done up above. Okay, we've discovered what that is. Substitute x equals 5 to confirm f dash of x equals 10 as in the previous question. That is exactly what I've just done. So I might just say C, previous question. So as you might remember, what I mentioned up above is that's the way I actually do it. We might actually have another look at how we could have done the first question, just to show that there are other options. The only difference would be the way we write this down. So let's write f dash of x is f of x plus h minus f of x over h. Just double checking that I got the rule right. Okay, so what we could have done is we could have popped our 5 straight in and had f of 5. Then we had f of 5 plus h minus f of 5 all over h. That's the same way. Instead of leaving it at the end to sub in, we could have subbed it in at the start. I personally think this way is easier, because that's what we're used to doing, but that's up to you. So this is the other way we could have done it. So our f of 5 would give us, if we put 5 plus h into our formula, we'd have 5 plus h all squared minus x squared, which was 5 subbed in, 5 squared, all over h. We open that up. Same as before, square the first. You can pause it and FOIL it if you like. Okay, I'm going to do it this way. Square the first, square the last, plus 10h. Oops, sorry, minus 5 squared at 6 o'clock in the morning while I'm doing this, so my brain's not quite awake yet. Let's see if we can work that out. Okay, crossing these guys out, because they cancel out, we're left with a 10h plus h squared over h. Take the h out the front. 10 plus h over h. And we're left with 10 plus h. So if we take the limit as h goes to 0, remember h is not going to equal 0. It's tending towards 0, but never really getting there. We get approximately 10. So that's all that was saying was, hey, we could do it both ways. Personally, I like that first way better, and that's how my brain thinks it through. Let's differentiate and let's put our function values in. Okay, let's look at 4, and that's our last one for today. Find the derivative of f of x equals x squared plus 4x via first principles. Let's write the rule down first. Okay, I've got the rule down. I've written a little bit different to last time. I've put the limit in the rule, which I hadn't written up above. Doesn't matter too much if you don't pop it in the front, as long as you remember at the end that we are limiting it. But I'm going to pop it in there like that this time. So our f dash of x is a limit of h goes to 0 of f of x plus h minus f of x over h. Here's our f of x. To get our f of x plus h, we are just going to replace our x with an x plus h every time we see it. So we're going to have x plus h all squared plus 4 lots of x plus h. That's what I've got to start with. I'm going to take away 4 lots of, not take away 4 lots of x plus h. That's our f of x plus h. We're going to take away this, our function, x squared plus 4x. And this is where we need to be really careful because we're taking away the whole of the function here, okay? Taking away the whole of the function means when I open those brackets up, I should have that minus into each of those terms in there. And that's all over h. So here's where your algebra comes into play a little bit, okay? Remembering that. So let's open our brackets up, get the like terms. I'm going to keep going ahead. You might want to pause that video while we do that. There'll be a little bit of thinking time for you then. So I'm going to open that first bracket up. And there's that first bracket. Multiply by 4 in the second bracket. And then take that minus through both of those terms in that last bracket. So it is long, okay, and you're going to have to be really careful. We've got x's, xh's, h's, h squared, so it's a very long one here. We just need to work out carefully what we need and what we don't need. Okay. So 2xh left, h squared, 4h, and all over h. I'm going to pull the h out of that top line now. So I'm left with a 2x plus h plus 4. All over h, which gives me a 2x plus h plus 4. Okay, I'm going to have to squeeze this in over here a little bit, but our f dash of x, taking our limit as h goes to 0, but h not equal to 0, and we can pop that in there as well if you like. So that part there is going to tend towards 0, so our f dash of x is going to tend towards f of x plus 4, and that's what we're going to work for in our next part. Work with. Okay, so that's our f dash of x. Let's use that for b. Find the gradient of the tangent at the point 1, 5 on the curve y equals x squared plus 4. So remember, gradient of the tangent is our derivative. It's our f dash of x. We've already done that. We've just used first principles. Okay, remember those functions are the same. So we've already done that. At the point 1, 5, well, we've got x equals 1, y equals 5. So I'm just going to pop b over there to fit it in for us. So we are going to pop in to f dash of x, our x point. 1, 5. So we want to find f dash of 1, which is 2. Oops, I don't need that little bracket up the top there, do I? Sorry. Get rid of that little guy there. 2 lots of 1 plus 4, which is 2 plus 4, which is equal to 6. So that's our gradient of the tangent to the function at that point. I'm going to just double check that that's all we needed to do. That's all we needed to do, and that's the end of that video. That's going to allow you guys now to go back. We have a look in our little schedule and have a go at 8b and work through a lot of that. Just the earlier questions. If you're going to be doing extension next year, have a go at 11 and 12, but mostly let's have a go at those earlier videos. And that's all for today.